Hi everyone, and welcome to the video abstract on Hall spin manipulation in inhomogeneous and non-separable electric fields. This was published just a month ago in PRB. So let's get started. This work was basically focused on germanium holes. Germanium holes are very interesting creatures for quantum computation. You can use the spin, use for defining your qubit, and you can use electric fields to manipulate your spin by taking advantage of the spin-orbit coupling in these devices. And well, there are already very nice demonstrations in both silicon and germanium. There's a 4-qubit processor in Delft, where they have shown very nice single qubit gates and 2-qubit gates. And well, one interesting thing about these works is that they were able to manipulate the spin within plane magnetic fields. However, the conventional theory says that in these planar isotropic quantum dots, you expect cubic Rashba. You also expect a GTMR mechanism to manipulate your spin, but when the magnetic field is in plane, these two mechanisms are not very efficient. So there was something missing, and we tried to solve this problem by performing realistic simulations of germanium devices similar to those that were in the experiments. So for this, we design our device and like this, and we solve the Poisson equation to get the electrostatics right. We get the convoluting Hamiltonian for the hole, and we extract the G matrix as a function of the gate voltages of the different gates, so we can use the G matrix formalism to extract Rabi frequencies. And what we observed in our numerical experiment is that, yes, there is this background of Rabi frequencies as a function of magnetic field orientation. And when you are at vertical magnetic fields, you have a local maximum, which is consistent with cubic Rashba. But we also have a feature in plane. And this feature in plane can even be the maximal Rabi frequency, the optimal way of manipulating these qubits. And well, so there was something that was going on. One peculiarity of this is that even at zero vertical field, this feature is still there, so it's not Rashba. And we found that the key ingredient for this physics, for this feature, was that the confinement potential was actually non-separable. This is something that you can actually model yourself with this kind of toy model, and if you go ahead and do this modeling of the confinement potential, the in-plane confinement potential, depending on the vertical electric field as it happens in reality, that you can go ahead and perform perturbation theory with the convoluting Hamiltonian and extract an effective Hamiltonian for your heavy hole that can now couple can now allow Rabi oscillations when the magnetic field is in plane. It will be very similar to a GTMR mechanism in the sense that you are deforming the dot inside this non-separable electrostatic field. So, we also checked different possibility, the possibility of driving with a nearby gate, just with one of them, and we found that you can optimize the Rabi frequency. You can enlarge them by a factor of 3, 4 by just driving with this gate, but then the Rabi pattern, let's say, as a function of magnetic field is a bit different. Anyways, it's the optimal way. So well, with this, I thank you for your attention, and please check out the paper if you are interested. Thanks.